Everyone knows that the universe we live in is vast and empty, but if you ask how empty the universe really is, many may not have a concrete idea. In fact, the degree of emptiness in the universe is likely beyond your imagination. To illustrate just how empty the universe is, let's start with the Earth and the Moon. Usually, we imagine the Earth-Moon system to be like this, but in reality, it's not like that at all. The average distance between the Earth and Moon is about 380,000 km, while the radius of the Earth is about 6,371 km, and the radius of the Moon is about 1,737 km. So the true situation of the Earth and Moon should be like this. As you can see, there is a much emptier space between the Earth and Moon than imagined. So what can fit in this space? Yes, just between the Earth and Moon, you can fit all the planets in the solar system except for Earth. After the Earth-Moon system, let's look at the solar system. Here's a diagram. The outermost layer of part 1 is the orbit of Jupiter. The outermost layer of part 2 is the orbit of Pluto and the Kuiper belt. The outermost red orbit in part 3 belongs to the dwarf planet Sedna, with its perihelion about 76 astronomical units from the Sun and its aphelion about 937 astronomical units from the Sun. The outermost layer of part 4 is the Oort cloud, with its inner edge 2,000 to 5,000 astronomical units from the Sun and its outer edge about 1 light-year from the Sun. Once out of this range, it can be considered to have flown out of the solar system. It should be noted that the Sun occupies about 99–86% of the total mass of the solar system, while the remaining mass is mostly occupied by the 8 major planets and their satellites. The minor bodies running in the solar system are actually much more sparse than imagined. Even in the dense asteroid belt, the average distance between objects is still about 770,000 km, much farther than the distance between Earth and Moon. Seeing this, I believe everyone now has a concrete idea of how empty the solar system is. Okay, let's look at the Milky Way galaxy. The stars in the Milky Way are very unevenly distributed. Specifically, the farther from the center of the galaxy, the lower the density of stars. In the core region of the Milky Way, the stellar density can reach 289,000 stars per cubic light-year, while at a position 100 parsecs, about 326 light-years, from the galactic center, the stellar density drops to 2.9 stars per cubic light-year. In the region where our solar system is located, the stellar density has dropped to 0,004 stars per cubic light-year, and in the edge regions of the Milky Way, the stellar density is even lower, down to 0,003 stars per cubic light-year. In total, the average stellar density in the entire Milky Way is about 0,006 stars per cubic light-year, which means that in the Milky Way there is only about 1 star per 167 cubic light-years, and the average distance between stars is about 5.5 light-years. To help understand the degree of emptiness in the Milky Way, let's hypothetically take 2 stars the same size as the Sun, with a distance of 5.5 light-years between them. If we shrink these 2 stars to the size of a soccer ball, then with the same proportion, the distance between these 2 soccer balls would be about 8,223 km. Observational data shows that the degree of emptiness in other galaxies in the universe is similar to the Milky Way. More importantly, the distances between galaxies in the universe are typically on the order of hundreds of thousands or millions of light-years, and the matter in the vast spaces between galaxies is extremely rare, almost a complete void. In addition, there are many cosmic voids in the universe, where the number of galaxies is extremely sparse, or there are no galaxies at all. These voids are usually very large, some even larger than you can imagine. For example, at a position about 700 million light-years away from Earth in the direction of Bootes, there is a Bootes void, with a diameter of about 250 million light-years, spanning about 0.26% of the entire observable universe. With galaxies already so sparsely distributed in the universe, the existence of cosmic voids further increases the emptiness of the universe. As mentioned before, galaxies themselves are already very empty, and all these factors combined make the universe extraordinarily empty. But just how extraordinarily empty is it? To describe the emptiness of a region of space, matter density is undoubtedly a good indicator. In theory, we just need to measure the volume and mass of the universe to calculate the matter density of the universe, but obviously we simply cannot do that. So we have to make do with the matter density of the observable universe. From the macro perspective, matter in the observable universe is distributed uniformly overall, and since the volume of the observable universe is known, we just need to measure the mass of a portion of it and extrapolate that to estimate the matter density of the entire observable universe. This is how scientists have estimated in past research that the matter density of the observable universe is about 6 protons per cubic meter. What does this mean? Let's put it this way. Imagine a cubic box with edges 1 meter long, containing 6 protons. Now if we enlarge the protons inside to the size of a common glass marble, diameter about 1.5 cm, then with the same proportion, the edge length of the cubic box will be enlarged to about 90 billion km. In comparison, the average distance between Pluto and the Sun is only about 5.9 billion km. In a gigantic cubic box with edges 90 billion km long, there are only 6 glass marbles with a diameter of about 1.5 cm. This can be considered the degree of emptiness of the observable universe. Pretty beyond your imagination, right?